is there a desire for more customizability, like beyond kind of the current, like, I guess, offerings, right, in terms of these different sizes of chips? And is maybe that a niche where smaller companies can enter to kind of fill that gap?
Yeah, so actually that's a very good question because there are two types of chips now. These are the custom chips that you just mentioned. Most of the chips we hear about are Intel processors and memory made by Micron or made by Samsung or made by those. And these are the only ones that we know about. But in your car, there are hundreds of chips, for example. There's a chip in your tire, that measures the pressure, for example. So these chips are very simple chips. They're not hundreds of billion of transistors. There maybe you have 1,000 transistors. They maybe have very small chips. So these are called.
Hello, everyone. Welcome back to the It's a Material World podcast. I'm Puneeth, and this is David. How's it going, David? Anything new going on?
Pretty good. Yeah, I just started looking for some new apartments. My lease is almost up, so
Already?
yeah, I'm
Wow.
got to go around the city and check out some new things. So very exciting. What about you?
Yeah, I not anything regarding moving, but this past weekend I went to Miami, just for like a 4-day weekend, having some fun there. And yeah, it was a ton of fun. Some pool parties, got to go to the beach and just explore the city. So yeah, had a good time. But to get into the episode, we talk about semiconductor manufacturing, as you can see in the title of this episode, but more so kind of going against the grain, talking about the bottom up additive manufacturing approach, whereas current methods involve a top down process with etching. So just wanted to hear from you first. Is there anything that stood out to you or anything that you found particularly interesting that Dr. Busnaina discussed?
Yeah, our guest is super knowledgeable about semiconductor manufacturing. He's been in the field for tens of years, and I think it's just really interesting to always hear a subject matter expert who deeply understands what's going on, talk about what he's passionate about. So I thought just his overall knowledge and excitement were very interesting to hear about, as well as the technology of bottom-up additive manufacturing. And so the idea is that right now you code a bunch of layers and then you etch off the parts that you don't want. His approach is just like 3D printing. You can functionalize the silicon to make sure that your particles will only stick where you want them to. And you can deposit particles just on that. And so he talks about how much more efficient it is and how much faster iteration and cheaper it is to make. And so that was all very, very interesting to hear about, especially because semiconductors in that industry, you hear all the time about how expensive it is. And then with vehicle makers, they're always a chip shortage. We hear about that all the time. And so hearing about this new way to potentially make some chips was very interesting. And I guess the second thing that was very interesting was he talked a little bit about the breadth of the technology. So he described exactly where we are in the field and exactly what this bottom of additive manufacturing can address up to a certain granularity. And so it doesn't meet cutting edge, but at the same time, we don't have to, just because this new way can help with R&D and be faster at iterative cycles. And so I thought that was also interesting to hear how he didn't have to address the very forefront of the problem. There's other problems within the entire scope that this new technology could completely revolutionize, which I think is somewhat also against the grain, as people usually think of new technologies only addressing the foremost problems of the field.
Yeah, for sure. And just to give kind of some comparisons, right, with the typical fab, there's several pieces of equipment that cost, $5 to $15 million each, whereas this potential process, right, has just one piece of equipment that kind of does it all and only costs $1 to $3 million, right, while still showing those improvements in efficiency. So there's a lot of potential. There's a lot of upside in this bottom-up approach. One other thing that I wanted to just discuss, and this is something that Dr. Busnaina and we talked about kind of after the recording, but I wanted to bring it to this intro, is how important it is to really learn the fundamentals of defects and yield. It's something that he teaches in his coursework, and he gets calls from semiconductor manufacturers all the time about, hey, do you have any students who really understand defects in yield? Because then it helps identify the root cause of some of the issues that those companies are facing, right? Like yield is perpetually a concern. It's something that they always want to improve, and it's not commonly taught, or it's not taught in depth in a lot of material science courses. So that's just something for our listeners to potentially keep in mind if you're interested in semiconductors or electronics, is to try your best to gain that fundamental, those first principle understanding of materials defects and yield. And potentially even look into talking with Dr. Busnaina about gaining a better understanding of that, because that'll help differentiate you when entering the industry. Outside of that, is there anything else you wanted to mention before we get into the episode?
Nope, just always interesting to hear him speak, and he's very passionate, which is always a good thing.
For sure, for sure. But yeah, we're closing in on 100 episodes. Thank you guys for joining us along for the ride. Feel free to subscribe if you enjoy this episode on your favorite podcast platform, and leave a rating and review. It would really help us out. So without further ado, let's get into it. Hey everyone. So for today's episode, I am happy to introduce Dr. Ahmed Busnaina, who has really done it all. After getting his PhD in mechanical engineering from Oklahoma State University, he immediately started his long career as a professor. He has been a professor for nearly 40 years, with professorships at San Diego State University, Clarkson University, and his current role at Northeastern University, where he has been for over 20 years. In 2016, he founded Nano OPS Inc., a new company focused on printed micro and nano-electronic devices. Dr. Busnaina also had a 20-year career in industry as a consultant for both IBM and Lawrence Livermore National Lab. Thank you so much for coming on the podcast today.
Thank you. Thank you for inviting me.
Yeah, like Puneet said, you had quite a long career with many different roles. Could you briefly describe your professional career path, about how you transitioned from academia to industry to founding Nano OPS?
Thank you. Yeah, it's a sort of a unique and different career, because during my PhD, most of my work was on fluid dynamics and combustion, and my PhD was funded by the U.S. Air Force and NASA, and so part of my PhD is to actually develop a modeling software for computation fluid dynamics, which at that time there were no software packages available, so you have to write the code yourself, do everything yourself. And so I worked on modeling and redesigning gas turbine combustors for jet engine. And once I graduated, got my PhD, I still pursued that, but there wasn't a lot of funding in that area. So I started looking at other applications, and I got connected with IBM in Burlington, Essex Junction, Burlington, Vermont. And at that time, they were scaling their manufacturing process, semiconductor fabrication, from 5-inch to 8-inch. At that time, there was no manufacturer that made 8-inch. So I used the same modeling techniques and my knowledge in fluid mechanics and chemical reactions and so forth to scale up a lot of their processes. And so that developed into a working relationship. They said, and this was involved modeling as well as doing experiments. After that, they wanted me to look at other processes, such as electroplating, copper, chemical and mechanical polishing. Then it went from there to work with Intel, Applied Materials, Motorola, Micron, a variety of other companies to look at other processes, deposition of tungsten interconnect, tinitide, a lot of different things, and then developed into looking at defects, because defects is a big, huge problem in semiconductor fabrication. So I specialized in that for almost 15 years or more, 15, 20 years. I still do that, still get invited by industry to talk about this, which we have not done for a while, but I still do that. About 2004, 2005 timeframe, when the semiconductor manufacturing became very expensive, I started looking at another alternative way to make electronics, and we got inspired by nature. Nature builds things bottom up, and so we said, well, is it possible to build things bottom up instead of top down? And that means we start with very small, tiny building blocks, like nanoparticles, for example, and start building structures from there to build electronic circuit and a chip. And so we worked on that from 2005 until now, and that led to the startup Nano OPS, which was started in 2016, which was actually built to commercialize the technology and to build equipment that utilize this technology to make electronics.
That's awesome. So for our listeners, we haven't really dove into like the semiconductor fabrication process in too much detail. So before we get into Nano OPS and kind of revolutionizing that process, can you briefly describe currently used techniques within the semiconductor industry, what exactly that top-down approach is?
Thank you. Yes, top-down means that you don't have anything guided by, you sort of everything comes from the top. So since the semiconductor fabrication started and making circuits on basically the electronics as we know it started with components like transistors, and those are you old enough to remember when you open a transistor radio, you'll see different components and you don't see chips. That didn't come out until about 1970 when you have integrated circuits. And so these components were all made using vapor deposition or gas-based process, and that means that you have to deposit using a chemical reaction or using a physical reaction to make atoms deposit a material, like for example, let's say copper or aluminum or as conductor, and then you deposit the insulator and so forth. And so basically what you do is you start with a silicon wafer, then you deposit oxide, then you use lithography to pattern it, and that means covering the areas you want to keep, and etching, and that means, and then you go into an etching process where you remove the process. So it's not an additive process because you coat the whole wafer with, let's say, a film, and then you etch most of it to leave only the circuit lines or patterns that you need for that layer. And you repeat this all the time. And now we make up to 30 layers or more, for example. And so you're constantly depositing material and then removing it, with the exception of the ones that you want to keep. And so that's the process. All of it was gas-based until about the late 80s, 1990s, when copper was very difficult to deposit using a gas phase process. And then the copper electroplating was introduced, which is liquid-based. And so the gas phase process also occurs in vacuum. And so you need a lot of vacuum pumps, high vacuum in many cases, where you need 2 vacuum pumps actually to reach that high vacuum. Where liquid-based, of course, just liquid, it's atmospheric pressure. So basically, it's a top-down process where you keep depositing complete film and then etching it to leave only the circuit. And then you deposit the other layer and the other layer and the other layer and so forth. And so it turns out to be very expensive, very power intensive, because you need a lot of power for the vacuum pumps. You need high temperature in many of these processes. And so as a result, the fabs used to be reach close to 1 billion in the early 90s. And then now a fab will cost over 20 billion. Some cost 23, 24 billion dollars.
That's kind of crazy. Could you kind of elaborate more on maybe how your research is tackling the problem of the bottom-up approach and why it's so different than this top-down approach that you just explained?
Well, first of all, the bottom-up is additive, which means we don't actually etch or remove anything. We just deposit exactly the circuit layer that we want. Let's say, we have a resistor like that's copper, for example, and you deposit that. If you're doing a transistor, for example, you deposit the different parts of the transistor, which are 4 layers, and basically you don't remove anything. With the semiconductor, traditional or conventional fabrication, you're always depositing and etching. And so there's no selectivity whatsoever. The bottom-up actually is really inspired by nature, because in nature, if you have a tree, for example, you have a seed and that goes, the tree goes, and it's guided by the DNA and the seed and so forth. Human being also, so with the seed and the grow. And so the question is, why can't we make things that way in electronics? And starting with particles, for example, and just so we don't have a DNA, we sort of functionalize the surface of the wafer to make sure that the particles land where they do, and then we use something like electrostatic force, magnetic field or optical field to guide the assembly, and then the assembly grows just like a tree, and it goes in and you get your structure. Instead of blanketing everything with a very bulk material and then try to etch to get that small structure. That's the basic difference between the two approaches.
We'd love to hear. So that's it's a very novel approach where now you're saving so much material. Could you compare the two between top down and bottom up? Of course, it sounds like you'll be much more efficient. Do you have any numbers about how much more efficient? And then also, are there any effects on the final properties or performance after this different processing approach?
That's a really very good and perceptive question. So let me address the first part. So we know we did calculations, for example, and we know we published looking at the carbon footprint, for example. That's the first thing we started. It's really related to how much power, but not just how much power the process takes, but how much power goes into making the liquid, how much power goes into making the gas that you use, for example, how much power goes into making the particles you use, how much power goes into the machine you use. So we did that, and we did that, this was some time ago when our process was really very slow, and found out that our manufacturing process compared to the semiconductor fabrication has a 10 times smaller carbon footprint. Now we speed up the process. So now it's about 20 times smaller carbon footprint. That's one. The power, if we just look at the power, one fabrication facility uses as much as 50,000 homes in a year, power-wise. So it's like a small city. The waste, for example, the material used, because it's very selective, you're not actually depositing a layer of films and then etching most of it. It's about 1,000 times less material used in making the same circuit. So, for example, let me give you just a quick example. If you look at your iPhone, there's a glass, and then when you touch your iPhone, you can control the apps and print and type and so forth. And so the iPhone actually has a Gorilla Glass, which is made by Corning, and underneath the Gorilla Glass, there's a PET substrate, a polymer substrate with a copper grid. This copper grid has about 2 micron lines with a spacing is about 100 to 200 micron, depending on the design. And so it's like a grid. And that grid, basically, when you touch the glass, that grid senses the charge, and that charge goes to activate the app and so forth. And so the way they make this is that they sputter copper over a web of polymer. That's a polymer that goes under the glass. And then they etch 99.99% of that copper. So there's a lot of waste in that process. For example, when we did this, we demonstrated that we, of course, only use the material that goes to the grid only. We did not deposit material anywhere else.
So you mentioned, just again comparing it to kind of the current methods and the current fabrication process, you mentioned it costs billions and billions with a B dollars to set everything up, right? With all the equipment, et cetera. I was just wondering, what would that look like? Let's say, we fast forward, we have a whole fabrication, or we have a whole semiconductor fab with this bottom up approach additive equipment. What would the cost potentially look like for that?
So that's a good question, because it goes into so many aspects of this. So for example, one of the other aspects that we didn't talk about is when you order a chip, and we actually, I did order chips from TSMC, which is the biggest semiconductor fabrication. TSMC is Taiwan Semiconductor, manufacturing corporation. It's the biggest chip manufacturing. It's a contract manufacturer. So all the Apple chips are made there, for example. Even Intel actually makes chips there. Because they're ahead technology, manufacturing technology of Intel and others. And so I remember we ordered very simple chips, very specialized custom chips back in 2010, and we had to wait almost a year for their order. And now the order, you have to. So imagine you're designing your chip, and then you wait 18 months just to test it. And so using this technology, you can make your chip the same day, or in 2 days, or the same week. And so the development cycle is very short. And that means you can innovate very quickly, and you can do things that will take 10 to 20 years to develop. You can do them in 1 year. And so that's one aspect. And that's because we put all the processes in one tool. So instead of using about 20 or 30 pieces of equipment, each one costs about 5 to 10 million to 15 million, and some cost more. You just have one piece of equipment that costs just between 1 to about 3 million, for example, but then it does everything. You just put your design, you put your material, you put your other chemicals that you need to use, and you put your substrate, wafers or glass or whatever you want to print it on, and that's it. And you let it go. It's fully automated, for example. So that's what Nano OPS has been working on, making this process so simple that you don't really need a PhD to do it. You just basically, once the process is optimized, then you actually use the tool and use it to make chips, and have your chips done at least in just a day or two.
So I guess something that I asked before that I want to revisit is, so yeah, when we think about the MSE like tetrahedron with the 4 points, so you're changing the process. And so have you been able to notice any changes in performance, or is it literally almost the same from one process to the other?
That's a very good question. Actually, it's definitely not the same, because in the other process, you're actually using, what do you do? Deposit. You either deposit atoms or molecules. And so you deposit very, very small, and so you get a very nice film. Everything goes well. You have a solid film, sometimes single crystal, sometimes polycrystalline, depending on the need and the process. That's not the case with our process. And so the goal for our process is to actually get there, get exact same material structure, material properties, because that's how we duplicate the same performance. So it starts with the materials. You have to get your material to get there. So we have demonstrated, actually, we published, didn't publish all that work, but we published a lot of it. And so we have shown that depending on the process and depending on the particles you get, you can actually start with nanoparticles and then build them up to get a single crystal. So we showed that gold, we showed that in silver, and these are at room temperature, by the way. Depending on, you use forces, basically forces that are there already, and you're just applying a little bit of force using electrostatic field to push the particles together, and that leads to a single crystal, which is the ultimate, basically. That's what, for example, like let me just briefly explain why single crystal is important. So all the semiconductor, all the computers, all your laptops have chips, and these chips have transistors, and these transistors will not have high performance unless they are made from single crystal silicon. Okay, so you really need single crystal. You certainly can make transistors that's polycrystal, not single crystal, but the performance is going to be like 1,000 times less. And so basically, it's very, very important to use high-end electronics. You really need single crystal. So we have shown that you can actually start with particles and get single crystal. In some cases, depending on the particles that you start with, if they're tiny and single crystal, you can get single crystal even at room temperature. If they are large and not single crystal, then you need high temperature, up to 1,000 degrees treatment, and then you can get single crystal. So it is possible to get actually single crystal, and that means that we're matching exactly what happens in the semiconductor. There's still a lot of development that's needed to actually scale that. We've scaled it to large, but to get something like that's not single crystal, for example, like for metal, for example, for like amorphous or polycrystalline material, you can get that easily. Single crystal is still hard to do, but it is possible because we've shown that for a few materials that it can be done. So the answer is we're not there yet in terms of getting high-end electronics, but we're focused on doing components and simple chips, because then you can do them very quickly, and that means custom chips. It'll be very easy to do.
And there seems to be a lot of potential and upside, which is something that I wanted to briefly touch on with your experience founding Nano OPS. I believe you mentioned in a previous call that many venture capitalists are hesitant to invest in this type of, upscale or high scale manufacturing, since it has that high cost and that significant investment upfront. So can you touch on kind of what you would say in return, right? Like, what is the upside to this process that makes the return on investment definitely worth it?
Thank you for asking that question, because it's really difficult. If you look in general to the venture capital, for example, they fund typically, medical or bio applications. They're very, very good. A very large number of them do that, or software based. Mainly because the capital investment startup is very small. In software, you just need good, computer equipment. In bio, you need really a bio lab and chem lab. But if you're making electronics, you need equipment, you need robots, you need large, and also you need a lot of development, which costs money. And so they usually for example, like even a simple startup could, a seed fund could be 5 million or more, for example. So because of that, they back off. And as one of the founders told me, that if your process, it's very easy to raise funds if you have customers, paying customers, or if the technology you're developing is so far away and not very well defined. And so that we are in between. So everybody expects us to make chips or have lots of customers before they invest. And I'm saying, if I'm getting to that point, I don't really need your investment. So basically, and also the business model for us is two business models. One is to make the chips, but that needs a plant, a factory, manufacturing plant. And that actually requires a lot more money. Or to make the equipment, which what we're doing. That still requires money, but you can work with partners that will make the equipment, that will do the software. And so that's where we're going through right now. But the investment is really difficult to do because we are at the point where everybody wants us to provide the details of the material, and not only that, but to actually make devices, and they test these devices, and that gets to be very complicated, much more involved. And so and the problem for us is that we have to spend a lot of money to do that, and they're not paying for that money. They just want for the results. So we went through a couple of VCs. The first one actually was very generous, Analog Devices, that made investment, and the other one did not pay any money, typical VC. We got hit with COVID, and then they pivoted to other applications, bio applications.
Interesting. So I'm sure one of the biggest questions that a VC will have for you is how scalable the technology is. Of course, like you've mentioned, you're like so much more efficient, but to get it out there and mainstream, what do you have to overcome? And then how scalable do you think it'll be like once you figure out like quality and the process down to a science?
I started in scaling back in '86 with IBM, where we had to scale the process 5-inch to 8-inch. And at that time, believe it or not, we were getting equipment from the biggest equipment makers in the country, in the US. The equipment was scaled, but the process was not scaled. And so that's why I started working with IBM, and they asked me to scale the process for them. So that's a very important part of it. And so as a result, when I started looking at this, that was the first thing on my mind. So if somebody brought a process, by the way, this was driven by, was funded by NSF and DoD, this whole event. And so we had a center at Northeastern University that was called NSF Nanoscale Science and Engineering Center for High Rate Nano Manufacturing. That's how we developed this process. So there were about 100 graduate students, about 30 professors, and about 20 postdocs plus that actually worked on this. And that led to a lot of publications, a lot of patents. We have the Nano OPS licensed 35 patents, and there are still 40 other patents that came out of the center. And so when we started this center, when somebody suggested a process, for example, like a tip-based process, like an AFM, you can certainly use an AFM and coat the tip with material, and actually you can write nanostructures, and people have shown that. But that is not scalable. You cannot actually make billions of transistors it takes hundreds of years actually to do that. And so we focused on things that are scalable. For example, if I apply electric field that's guided by some functionalization on the substrate or some pattern on the substrate, then I can apply it on the whole wafer at the same time, for example. And that means my fabrication time is very, very short. We got the process to be, so you can actually print a circuit layer on a whole wafer in 1 minute. So basically, from the very beginning, when we started looking at the directed assembly processes that we adopted, the bottom-up processes, we actually excluded the ones that we thought fundamentally cannot be scaled. We only focus on the ones that can be scaled. And so, for example, a 4-inch wafer to make a circuit layer on a 4-inch wafer takes about a minute. For an 8-inch wafer, it's linear. It takes 2 minutes, for example. A larger wafer will take a little bit more time. And so our process was always scalable, and we always kept an eye on the throughput because we know that if you don't have the throughput, it's not going to be commercialized.
Interesting. And so you talked about kind of like the size of the chips, the semiconductor chips, and there is that general question, even with current technology, the question of size limitations. How much smaller can we get? Right. And so, we have those conversations about Moore's law. So I just wanted to get your insight. How close do you think we are with current semiconductors to reaching the physical size limit? And is there any differences with your technology?
Yeah, so that's a very good question. So let me address just the scale first, the Moore's law. So when I first started working with IBM, the minimum feature size was 1 micron. And this was the 4 meg and 1 meg chip, DRAM. And that was the best chip that you can buy on the market. All the others were 16 kilobyte and very, very small chips at that time. That was right after the IBM PC came out. The IBM PC actually did not have those chips. It wasn't until later. But anyway, so at that time, it was 1 micron, which is 1,000 nanometers. Now, IBM just announced recently that they make a chip with 2 nanometer. So imagine, the scale change. And Moore's law basically shows that every 18 months, the number of chips will double. And so they did this by basically shrinking the feature size, and they kept shrinking until now. IBM showed that 2 nanometers. TSMC has production 5 nanometer for chips in production, for example, and they demonstrated 3 nanometer technology chips. And so you cannot actually go much smaller without very significant challenges for the material. Because remember, if you do 2 nanometers, for example, okay, a silicon dioxide molecule is about half a nanometer. So that means you're just having four molecules, and it doesn't take much. If you pass current through it nearby, the current could actually pull an atom from that line. And that happens. I mean, the electromigrations happen. So there are materials that can be easily separated. That's why the industry moved to copper, because it's more stable. And now they're going to actually move as the main conductor in the circuit. And now there's now a move toward cobalt as conductive material, because it's more stable. And so basically, it's going to be very, very difficult to go smaller than what we have now, like 2 nanometer. You're not going to be able to reduce it much, much further than that without actually sacrificing some of the performance and some of the stability. So what they're doing is building up, for example. And so basically, instead of having the transistor just at the bottom layer and then just build the interconnect on top, they're trying actually to build different layers of transistor. So stacking 3D. So basically, they're saying Moore's law is dead in 2 dimension, but it's alive in 3 dimension. Because Moore's law doesn't really talk about the feature size at all. It just talks about the number of chip per area. And so you can still revive the Moore's law by going in the 3rd dimension. And that means transistors on top of each other, for example. And so that's where the technology is moving. And you see that very clearly in the memory industry, for example. But part of this going really, really small, we run into another problem, which has nothing to do, it has to do with the feature size, and this is the defects. So the reason we work in clean rooms is because we want to make sure there are no defects, no particles, or nothing else that's foreign that lands on the circuit during manufacturing that could result in a short circuit or an open circuit. The circuit, when a particle lands in the middle of the path of a conductor, for example, and then so the current doesn't go, or a conducting particle can land and bridge 2 conductors, and then you have a short circuit. And then you have a defect. The chip doesn't work anymore. And so as you make your feature size smaller and smaller, and your chip size is still large, any particle that can land anywhere can actually cause a defect. So for example, the yield, meaning we do a percentage. So that means if yield is 90%, that means for every 100 chips you make, 90 would work, and you can sell those. So for example, a lot of the established ones like 50 nanometer or even we still make chips at 200 nanometer feature size. We still make chips at 80 nanometers and so forth. Those chips are 80 to 90 yield, for example, or higher. Some of the larger ones could go even to 99% yield. Guess what the yield is for the chips that do 3 nanometers and in that range? They're about 20 to 30%, which means 100 chips you make, only 30 or 20 actually got to work. And that's a huge issue, because that means your cost is actually making 100 chips, but you can only sell 20. And that increased the cost tremendously. There's another approach that's going on right now that actually was championed by DARPA a few years ago, about six years ago. And this is from going to this big monolithic chips like the M1 chip, for example, that Apple makes, that have multiple processor, multiple CPU, multiple GPUs, graphic processors, and memory, and a lot of different components. And they put them in one large chip. And because the chip is very large and you have very small feature size, the yield is low. And so what DARPA came up with a unique approach, saying, why do I need to make this chip large? Why can't I make take a CPU chip and a GPU chip and memory chip, and then take all these chips before they're packaged, they're still pieces of silicon, and then assemble them on another piece of silicon. And then that way I can make the same circuit. It's going to be a little bit larger, but I can make the same circuit, and I only use chips that are working, so my yield will be 100%, and then I can make them in a very short time. And so actually that after was demonstrated right before COVID, actually by DARPA. Now, and DARPA, of course, was focusing on DoD applications. Now Intel adopted it, TSMC adopted it, and a lot of people adopted it. They call it chiplet approach. So you take a lot of chips and make a larger chip out of those. And this needs three-dimensional heterogeneous integration of chips, because you can make all kind of chips. You put them on one piece of silicon, call it interposer, and that is basically saves a lot of money, makes the development cycles shorter. And so a lot of people are adopting it. And you'll see more and more of that in the products that we will use in the future.
Interesting. So I just had a question then about, you mentioned the different sizes of semiconductor chips. I was just wondering, from the industry perspective, is there a desire for more customizability, like beyond kind of the current, like, I guess, offerings, right, in terms of these different sizes of chips? And is maybe that a niche where smaller companies can enter to kind of fill that gap?
Yeah, so actually that's a very good question, because there are two types of chips now. These are the custom chips that you just mentioned. Most of the chips we hear about are Intel processors and memory made by Micron or made by Samsung or made by those. And these are the only ones that we know about. But in your car, there are hundreds of chips, for example. There's a chip in your tire, that measures the pressure, for example. So these chips are very simple chips. They're not hundreds of billion of transistors. There maybe you have 1,000 transistors. They maybe have very small chips. So these are called ASICs, the specific instruction chip. And those chips basically were very common in the 90s and early 2000. But then as the fabrication become more expensive, they became very, very expensive. For example, if I have a company and I need just about, let's say, 50,000 chips, okay? Well, the cost per chip is very, very high. I forgot to tell you that the custom chips that we made with TSMC, this is 2010, 2011 timeframe, we made 50 chips. It was $100,000 for 50 chips, for example. So that gives you an idea. And this was a very simple chip. It just had an amplifier, had very simple components. So because of that cost, the industry introduced another chip called FPGA, Field Programmable Gate Array, which means you have a lot of transistors and you can program these transistors to make any chip design you want. And so a lot of people were happy with that. A lot of people used it. But now these FPGA chips became really large and they consume a lot of power, and the size is not there anymore. Because they have to get the idea to actually have the capability to make it do anything you want. And so now people are going back to ASIC, but it's actually very expensive still to do that. And so the custom chips is difficult, but people are it's still economic based choice. And so now it's FPGA were very common and people like them, but now they're getting large and power hungry. And so people are actually saying, well, maybe I can do ASIC very cheaply. And so now we are in this situation right now where the big companies can afford to make ASICs because they can afford to have very large numbers, for example, like car manufacturer or so forth. But for a smaller company, it's very hard to do that. And so for our technique, you can make these things very, very inexpensively, because you can make your chip the same day. So that means that if I have a custom chip and I only need 1,000, that will still be affordable as compared to ordering it from a very large manufacturer where it'd be very, very expensive, because the setup for that manufacturing process is the same as if you're ordering 1,000 or 1,000,000. It's the same setup. So you're paying for that setup cost in the beginning, no matter how many chips you want.
So when we talk about like just technologies, new technologies, I think everyone's mind goes to like the absolute forefront of like what that field is working on. But I think you brought up a really good example with the car industry, is that there's a lot of simpler chips and we need a robust supply chain, or else we're going to have issues with being able to do all these simpler chips. So I guess the question for you and your company is the vision more towards just meeting consumer demand at all stages, or is there a focus on a size range or complexity of the chip that you think your application would be best suited for?
That's a good question. The problem for a company, you have to have income, and you have to have customers. So basically, to look at the big picture and not look at the financial at this point, this technology, we have shown that we can make transistors. We have shown that we can make all the components. So, for example, when I teach semiconductor fabrication to the students, graduate and undergraduate, I start by trying to simplify the process, explain what is it about. And so the best part, just to explain that, is to say that all the technology you have, all the computers you use, everything in your car and your laptop and your phone, all of it is based on 5 different electronic components. Only 5: transistor, diode, capacitor, resistor, and inductor. That's it. And I explain how each one of them work. And I'm saying whatever technology you have, you use, it's all made up of these 5 things. And so we teach them how to make these, using, let's say, bottom up or using top down, which is traditional manufacturing. And once they know exactly that a transistor is just a switch, it's on and off, and one is 0 and off is 1, and that's how you store your information. And a diode is just a one-way valve, for example, for current, and capacitor is just to store charge, and a resistor is just to induce resistance, and so forth. So it's very, very simple. So when you do that, then the technology become very simple. So when we started making this manufacturing technology, we started making these components first, and seeing how good can we make these components, and how can we match what the semiconductor industry use now. Then once you make those components, then you can go and make logic, make memory, make those, because all of them are basically a combination of all these 5 components. That's all you need. And so we actually did make logic gates, for example, like NAND. We made NAND, we made AND, we made inverters, we made NOR, and so forth. So those are NAND that's used very heavily in memory that we buy today, for example. So yeah, we can show that. So once you have quality, these 5 basic electronic components, once you can make them in quality and fast, then you can make anything else. It's just a matter of integrating them. And we've shown that can be done. And that opens the door to making, at this point, a simple simple devices, for example, like 1,000 transistor or 50,000 transistor or 100,000 transistors, that still can be made using this process. And by the way, we do bottom up, but we use lithography to functionalize the surface so that when we guide the particles, they land only at the right location. So because we use lithography, we can actually make structure as small as 20 nanometers. And we have demonstrated that.
Wow. Well, this was a super fascinating conversation, and I'm very excited to see, the next steps that you and your team take. But to maybe wrap up this episode, I was wondering, do you have any advice for MSE students that are interested in a career in semiconductors or electronics? Maybe, advice on classes to take, habits to build, or technologies to research?
Thank you for that. My degree is not material science, actually, it's mechanical engineering. And so, but I work with fluid dynamics, with chemical reactions, with material science, and so forth. So material science, actually, it's a very important. I mean, without material science, we will not have electronics today. So it's very important. So you want to basic material science, different any course in material science, actually, with the exception of the soft material like polymers and so forth, will apply to this technology. But also, I would recommend, on top of that, is to take a lot of manufacturing processes. Although manufacturing is addressed in some of these material science processes courses, but it's not really, doesn't put everything together, because you have a sequence of a lot of different materials. And in this sequence, you learn that the interface is so important between different materials, because it affects the interface. And so it introduces contact resistance. So even when you design the circuit, you look at the different interface between materials and pick the best material that will give you the least resistance, for example. So that's something that is not taught in material science courses, but not the focus in terms of how many materials you can put together and what is the best way to put the materials together, and how the current goes from one to the other and so forth. So these are very important, and you can get those by taking semiconductor fabrication classes and so forth. And by the way, once the structure is done, the differences between the way you make it is not that big, because you're still using the same material, and you're still using silicon, you're still using copper, you're still using silicon dioxide or high K material, which is hafnium dioxide and so forth, as an insulator, for example. I mean, that's the basic thing. For any semiconductor process, you need a conductor, you need a semiconductor, and you need an insulator. These are the basic three materials you need. And in some cases, you need to dope, which means make the semiconductor more conductive, for example, for certain applications like diodes, for example. And so basically, these are the very, I mean, if you put it in simplicity, it's very, very simple. You have 5 components that you know how to make, and you use to design any circuit or make any circuit. And then you have 3 different classes of materials: conductor, semiconductor, and insulator. That's it. That's all the semiconductor fabrication and electronics that we have today. Of course, it gets more complicated because you have complicated design. You have millions of transistors on the same chip, for example, or hundreds of millions of transistors or billion transistors. So that means you have to worry about the integration. You have to worry about the interaction. And so there's a lot of courses that deal with that, and not all of them are material science. So you have to branch out and take courses in manufacturing. And these will be very useful because it will tie in what you have learned in material science with the actual manufacturing process.
Got it. And I'm sure, internships in manufacturing facilities will help with that too, to get the hands-on experience, which is invaluable. Yeah. Thank you so much, Dr. Busnaina, for all of the insights you shared today. It was really interesting learning about the semiconductor processes and the bottom-up approach versus the top-down approach. But yeah, we really appreciate you taking time out of your day to chat with us. And again, very grateful for having you on the show.
Thank you very much for inviting me. This was a pleasure. Thank you.
As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.